All right, so thank you for the opportunity to speak here. And I should put an addendum on what Camila said. They're not quite H1/2, just a little bit below.
H1/2 minus.
H1/2 minus, so a little bit worse. And Euler equations is in the title of my talk, but for the purpose of the motivation part, I need to consider both Euler and Navier-Stokes. So the unknown is some velocity vector field u upper nu. I'll say what that parameter is in a second. Function of t and x. T belongs to some finite time interval, and x for me will live in the three-dimensional torus throughout this talk. And the equations look like this. So this is basically the balance of momentum in Lagrangian coordinates, and then we have the divergence-free constraint, divergence of u upper nu equals 0, and nu is a parameter which represents the kinematic viscosity of the fluid, so it appears in front of the Laplacian, and when nu equals 0, I get the Euler equations, and when nu is positive, I get Navier-Stokes. And my focus for today, similarly to Hyunju's talk from a couple weeks ago, will be solutions of these equations for values of nu which are small. And it is at these values of nu that we see what could be described as turbulence. So this is where we see turbulence. And of course, a complete description of turbulence is not something that I can hope to give you. What I will settle for is to pick a few properties of turbulent flows and try and exhibit solutions which have those properties. So the properties that I'm interested in are dissipativity. So let's say I want my solutions to be dissipative. As we'll see, that will mean that they have to be somewhat rough, so a lack of smoothness. And then I also want my solutions to be intermittent. And I'll tell you what each of these things mean, and I'll tie them into this function space that I have in the title. All right, so let me tell you what I mean by each of these properties so that we know what to look for in our solutions of the Euler equations. So all right, let's start with dissipativity. So if I have some solution of the Navier-Stokes equations you knew, I can compute the L2 norm to get the kinetic energy. And I can take minus the time derivative of this quantity. And for solutions which are dissipating the energy, I expect this to be some positive number. And I'm going to put brackets around this quantity to indicate that I'm either taking a long time average or an ensemble average. And then this quantity here is something that just depends on the parameter nu. And so I want to take the limit as nu goes to 0. And what we get on the right-hand side is some positive number epsilon. And this is the zeroth law of turbulence that Hyunju mentioned a couple weeks ago. And as we saw, this may be somewhat surprising because, at least formally, solutions to the Euler equations, so without the dissipative term here, should conserve this quantity. And so this is saying that we actually expect to see dissipative solutions in the implicit limit. All right, and as it turns out, in order for solutions to dissipate the energy in the limit as nu goes to 0, it must be the case that these solutions are somewhat rough. And a very nice, striking mathematical statement of this is contained in what we could call the Onsager theorem. So it was a conjecture of Onsager from 70 odd years ago, but we can basically refer to it as a theorem now. And what it gives is a dichotomy for weak solutions to 3D Euler. So this is only for 3D Euler. And it has two parts. So we're probably familiar with this here, but nonetheless, let me write down what it says. So the first part is a rigidity part. And it says that solutions in L3T B alpha 3 infinity x intersect C0T L2x are conservative if alpha is larger than 1/3. So are conservative if alpha is larger than 1/3, meaning that the time derivative of this quantity is 0 and the kinetic energy is conserved. And the proof of this is due to Constantine Urantiti after an earlier contribution by Iyenk. And one can see refinements or strengthenings of this statement in papers of Duchon and Robert, or Constantine, Cheskudov, Friedlander, and Schvidkoy. All right, and the second half of this statement is a flexibility result, and it says that solutions in C alpha Tx, I'll say, are flexible if alpha is less than 1/3. And by flexible, I mean that one can produce solutions for which the kinetic energy is not conserved. This was proven by Izet. In order to get solutions which are actually dissipative, one should refer to the paper of Camilo and Laszlo and Tristan and Vlad. And of course, one can also impose different kinds of pathologies on solutions in these regularity classes, such as an H principle. But let me not focus too much on the different flavors of flexibility. All right, so this is a very striking theorem, but I want to make a remark on something that it does not address, and that is the behavior of solutions in regularity classes which look like C0T H alpha x if alpha is greater than or equal to 1/3. Right, because I could have a solution which has this regularity, but not this regularity, so I can't apply the rigidity half. And the constructions of these solutions don't give estimates which lead to this regularity in L2. All right, so I'll motivate in a minute why one may search for solutions with this property, but this is a good time to state the main theorem that will be the focus of my talk. So this was joint work with Tristan, Nader Masmoudi, myself, and Vlad Vicol from last year. And what it says is that solutions in C0T H alpha x are flexible if alpha is less than 1/2. And of course, by the flexibility statement here, this is only interesting if alpha is bigger than 1/3. So that's the regime in which this gives a new result. And in order to motivate why one would look for solutions in this regularity class, I have to talk about the third property of turbulent flows that I'm interested in. And that is this property of intermittency.
So Matthew, this is for Euler, right?
Absolutely, 3D Euler. Yeah. All right, intermittency. All right, so at an intuitive level, intermittency refers to something which is not spatially homogeneous in maybe I should say homogeneous in time or space, because I could have concentrations in either the t or x variable. So you can imagine some signal which is constant for a while, then undergoes some severe deviations from the median, and then is constant again. And in order to tie this into solutions of the Euler equations or the Navier-Stokes equations, one could pose basically the following question. So I'll state it like this. So as nu approaches 0, in which function spaces does u nu remain bounded? And another way of saying this would be, in which function spaces should I look for solutions of the 3D Euler equations? And it is at this point that Kolmogorov's 1941 theory of turbulence figures in. He provided somewhat of an answer to this question. So let's say answer K41. So it's called the phenomenological theory because he postulated that the solutions enjoyed certain symmetries, translation symmetry and rotation symmetry, and a sort of self-similarity or scaling symmetry. And then from these assumptions and the assumption of the zeroth law, he deduced the following. So he said that the right function classes here might be LPT, be 1/3 P infinity X. And an example of a function which I should say for LP. And to give yourself an idea of what kind of function would satisfy this, you could consider a sum of sine waves, like 1/2 to the k on 3 sine 2 to the kx. So this is something which is a infinite sum of spatially homogeneous objects. And that homogeneity means that the regularity is the same, no matter which Lebesgue space I measure it in. And one thing I just want to point out is that it's somewhat striking that if I consider P equals 3, this space is exactly the space that was identified in the Onsager theorem. So what Kolmogorov is saying is that turbulent solutions of these equations are just rough enough to sustain anomalous dissipation, but not much rougher. All right, so intermittency figures in if we ask whether or not these predictions of Kolmogorov are correct. So question. Is K41? And I should say that the answer to this question could be divided into three parts. So the first part is the case P equals 3. So let's call this exponent alpha of P. So Kolmogorov says that alpha of P equals 1/3 for all P. And at P equals 3, what we see is that alpha of 3 is actually 1/3. And in the turbulence literature, this is known as the 4/5 law. And it's one of the few sort of non-trivial exact results that we have. All right, so experiments and simulations are pretty consistent about the P equals 3 case, but there are some deviations in the other cases. All right, so let's consider the case P less than 3. So this is something that people are still working on today, trying to figure out what the right regularity exponent is for different values of P. And what people sometimes find in the P less than 3 case is that alpha of P is greater than 1/3. And just to give you some baseline for what one might expect. So there's a paper of Iyer, Srinivasan, and Young from, I think, a year or two ago, in which they got something like 0.36 at the level of the L2 structure function, or I guess just the L2 Besov space, if you prefer. And this number, whatever it is, it's going to depend on the geometry of my domain, like if I flow past the cylinder or what have you. But this is sort of a rough guess as to what people see for P equals 2. And this, of course, then comes with deviation in the opposite direction when P is greater than 3. So this says that alpha of P should be less than 1/3. So a deviation in the opposite direction.
Can I just ask, what about the temporal regularity? Is it, so for instance, in this experiment?
Yeah, so the temporal regularity, I think, is LPT of B something P infinity X. So I think that's how these measurements are taken.
Is there any reason to expect any kind of like duality in alpha of P with respect to 3 or something like that? Or...
Yeah, because if I had that alpha of 2 was bigger than 1/3, but alpha of 4 was still 1/3, then by interpolation, I would get something which violated the P equals 3 case. So if you have deviations on one side in one direction, they have to go on the other side. They have to go in the other direction on the other side.
I like Holder conjugate or something like
that. So there's sort of different models for what these exponents should obey. And one of them, which I know just from looking at Frisch's book, it depends on sort of the fractal dimension of the solution. So I don't know if it gives you Holder conjugates, but it gives you something.
Sorry, so is this paper is numerical or is it?
Yeah, numerics.
Can I ask a small detail? Is this the Besov space or the density of the test function space?
It's a Besov space that I would just define using finite differences.
Just to be clear, you're not asking like for what values of alpha is it bounded, or you're still asking what the conservative thing?
I'm asking for which values of alpha is this quantity bounded, And whatever values I get should be consistent with the zeroth law. So dissipative solutions. All right, so my motivation really then in considering this regularity class is to show that the equations can sustain a wide class of solutions which are consistent with this particular deviation from Kolmogorov's predictions. All right, and if there's no other.
Can I have a question? So if P is equal to 2, right? I mean, isn't there some kind of connection with the 3/5 law or a 5/3 law?
Yeah. So the 5/3 law is the Fourier expression of the regularity statement B1/3.
That one is okay, right? 5/3.
So if alpha of 2 is indeed bigger than 1/3, then the 5/3 law, then that's saying that a solution doesn't adhere to the 5/3 law.
People would dispute 5/3 law.
Yeah, I think sometimes people do take it for granted that solutions do satisfy the 5/3 law. But yeah, I think there's probably some dispute.
Okay.
All right, so
Intermittency. Okay.
so that's sort of the backstory for this theorem, and I want to give you at least some sort of rough idea of how one might prove this and the sort of main tools and main difficulties that you'll encounter along the way. So, how to construct such solutions. All right, so the construction of these solutions proceeds via an iteration, and the iteration is on a parameter Q. So Q is the stage of my iteration. And at the Qth step, I posit the existence of a pair, UQ comma RQ, where UQ is a velocity field and RQ is 3x3 symmetric matrix. And UQ and RQ satisfy these equations. So UQ, I'll write the Euler equations pulling the divergence out to emphasize that I'm building weak solutions. And on the right-hand side, I put divergence of RQ. And then I should also impose that divergence of UQ equals 0. And in order for my iteration to succeed, I need that, so the limit as Q goes to infinity of RQ and L1. So by L1, I mean continuous in time L1 and X. All my spaces here are continuous in time, so I'll just write the function space in X from now on. All right, I should have that this is equal to 0, and I should also have the UQ converges to some limiting function U. And let's say the C0TH alpha topology. All right, and in order to achieve these goals, I of course need inductive assumptions coming with this pair UQ comma RQ. So let's say inductive assumptions. All right, so I'm going to write basically the simplest set of inductive assumptions that I can get away with. But in reality, what I will write is going to come with many more decorations if you want to do it rigorously. All right. So my first inductive assumption is that, let's say the maximum frequency of UQ and RQ is lambda Q. And lambda Q for me is A to the B to the Q, where A is a large natural number and B is basically 1 plus a little bit. So this is saying that I have just barely super exponential growth, but if you prefer, you can think of having 2 to the Q here, in which I'm saying that the first sort of Q Littlewood Paley shells of UQ and RQ are already defined at this step of the iteration. And I should, of course, have some kind of smallness assumption on RQ and UQ in different norms. So let's say smallness of RQ in L1, and let's say UQ plus 1 minus UQ in H alpha. And the smallness is something that's quantified in terms of this parameter lambda Q, but the precise definition isn't important for me right now. All right, so these are my inductive assumptions, and I want to propagate them to the next stage of the iteration. And in order to do so, I work within an ansatz. And the ansatz says that my velocity increment, I call WQ plus 1, is equal to UQ plus 1 minus UQ.
Wait, can I just ask a question on the map? What is the maximum frequency? It's really the boundary support, the Fourier support?
Yeah, morally speaking. In reality, what you do is you propagate many spatial derivative estimates where each spatial derivative costs lambda Q.
In which
L2 for UQ and L1 for RQ.
So it's not exact. It's not really like.
No, it's not honest to God compact support and frequency.
It has a little bit of that.
It has some tail. All right, so if at least morally speaking, I should expect that these guys have frequencies less than or equal to lambda Q, and these guys have frequencies less than or equal to lambda Q plus 1, then what this object ought to do is fill in the missing frequencies. So lambda Q less than the frequencies of this object less than lambda Q plus 1. All right, so my iteration then fills out the frequency support of the final solution, shell by shell. And let me work within a simplified setting. So for the purpose of making some toy calculations, let me say that RQ is E1 tensor E1 times some scalar function, which in an abusive notation, I'll just call RQ again. All right, and let me also say that RQ is positive because in a second I'm going to take the square root and I want that to be well defined. So my ansatz will look like the following. It will be RQ to the 1/2. And this is something which has frequencies less than or equal to lambda Q. And so I should multiply by something which is high frequency. And for me, that is this object script W, which let me tell you what it is. All right, so script W for me is an intermittent Macau flow. And I'm going to draw a picture to show you what it looks like, but these objects without intermittency were introduced by Laszlo and Sarah Denari, and they've turned out to be quite useful in a variety of convex integration schemes. All right, so what is this object? It's just a shear flow, a particular type of shear flow. So I'll say it's some function rho of the second and third variables times the vector E1. And let me tell you what rho looks like. So the support of rho, or I should say, the domain in which rho is defined is the second and third variables. So let me draw that. T2 in the x2 and x3 variables. And what I do is I divide my torus into periodic cells. And these periodic cells have the following dimensions. So this is equal to lambda q plus 1 times some parameter little rq, where little rq is in between 0 and 1. And rq, as we'll see in a minute, could be referred to as my intermittency parameter, if you will. It's the parameter via which inhomogeneities are introduced into my system. All right, so this is a periodic cell, and inside a single periodic cell, what I see is, let's just say a radial function supported in some little ball, and the diameter of this is lambda q plus 1 inverse. All right, so what's happening here? If RQ is small, then these cells are somewhat large compared to the size of the blue dot. So the support of this rho is a very small subset of T2. And if you compute what it actually is, support of rho has measure RQ squared. So this is where my sparsity comes from. It comes from the support of this thing. And I want some other properties on this guy. And what are they? So I should note that it solves Euler. That will of course be useful. And third, I want the mean of this object to be E1 tensor E1. And if I say that the mean of this W tensor W is E1 tensor E1, that's saying that it's normalized in L2 somehow, because this is a quadratic expression on the left-hand side and this is order 1. So in order for the object to be normalized in L2, because it has small support, it has to come with a negative power of RQ, which determines its size in a pointwise fashion. And if you just take these two properties and do a little computation, what you see is that the size of this object in LP is like RQ 2 on P minus 1. So I plug in P equals 2, and I just get something of order 1. if I plug in P equals 1, I get something which is small depending on the smallness of RQ. And I left some space here to say that I could take some spatial derivatives, and the spatial derivatives will cost lambda q plus 1. And that comes from the thickness of the support. All right, so these are sort of the main players in terms of my ansatz and my inductive assumptions and everything else.
So maybe you're going to say this, but how does the product compare to lambda q, so the previous one?
Say again?
How does the product of lambda q plus 1 and rq compare to the previous lambda? So is it much
The
still, or
lambda q plus 1 times lambda q?
times rq? How does it compare to lambda q, the previous one that you have?
Sorry, I still don't understand.
So you have this product that gives you the size of the box, right? Which is
Yes, yeah, I thought, yes, little RQ.
right. So how does it compare to the previous length scale, lambda q?
Yeah, I maybe should have put a lower bound on RQ, which says that lambda q plus 1 RQ is at least as big as lambda q inverse. All right, so we have an ansatz, we have a formula for RQ, and that means what we should do is plug in the ansatz and see what we have left. So we plug in WQ plus 1, and we use the UQ comma RQ solves an equation. So let's say solves star. And what we get is an equation for the new error term. And it says the divergence of the new error term, whatever it is, it ought to be equal to the leftovers that I get from plugging in WQ plus 1. And I'll divide those into 3 pieces. So I have my old error term, and I'll throw in here the nonlinear interaction of WQ plus 1 with itself. We call this the oscillation error. Then I have 2 more error terms, one of which is a material derivative of WQ plus 1 along UQ. And this is the transport error. And finally, we have this term, which is the Nash error. And the success of my scheme then means efficiently estimating somehow the size of these different things. And so what I want to spend the last 15 minutes or so telling you is a little bit about what goes into the analysis of these different pieces. All right. Let's go like this. All right, so let's start with the nonlinear error term. Let's start with oscillation. All right, so I'm just going to plug in what I know about RQ and what I know about WQ plus 1. And I get that os, if you will, is equal to. So I said that this was equal to E1 tensor E1 times RQ. And then I have RQ times W tensor W. And I'm going to split up W tensor W into 2 pieces. one is the mean, and the other is the identity minus the mean. And I've split this up in this way because I can exactly then cancel these first two terms using that the mean of this guy is E1 tensor E1. So these disappear, let's say by 3. And what I'm left with is the divergence falling on this term. And if I use 2, let's say by 2 says that this guy solves Euler. And that says that the differential operator is only going to land on this RQ. So let's say gradient RQ, identity minus mean W tensor W. And this is advantageous because a gradient landing here is a gradient landing on something low frequency, whereas if it had landed here, this has some high frequency. So this is why we use, part of why we use these objects.
It's actually luckier than solving Euler. No? It solves Euler with no pressure.
Yes, yes. Yeah. Yeah. If you plug in Mikado flows to, there's a system called the Euler alpha system, in which case these Mikados are still stationary, but they have some pressure and it complicates your life a little bit. So this is convenient. All right. And what I want is this to be equal to the divergence of some new error term, which means that I should set my new error term, let's say, which comes from this oscillation error. It ought to be the inverse divergence of what I have here. And you can think of the inverse divergence as a -1 order Fourier multiplier, although in practice, it's not convenient to use that definition in this setting, but nonetheless, it's a good ansatz. So -1 order Fourier multiplier. And this object, this -1 order Fourier multiplier, should pull out the minimum frequency of what's inside. And I'm imagining that this has frequencies lambda q, and this, I've subtracted off the mean, so it's going to pull out the minimum frequency, which is the opposite of the size of the periodic cells. So let's say this gains a factor of lambda q plus 1 RQ inverse. And this is where Bjorn's comment or question becomes relevant. I want a lower bound on RQ because if RQ is too small, then this becomes a useless estimate. But we encounter here, I guess, one of the main difficulties in this system. So let's say problem. If RQ is much less than 1, this estimate is going to be bad. I would prefer RQ to be equal to 1. And what you can check is that if for the purpose of heuristics, if you just plugged in RQ equals 1, you could do a few computations and you come up with a restriction on alpha and where is it? B. What you get is that alpha has to be less than 1/2B. And this is where the H1/2 threshold comes from. It comes from this error term. So even if RQ is equal to 1, there'd be no way for me to beat this threshold that I can think of. And as we'll see in a minute, taking RQ equals 1 is not acceptable, which means that I have to ameliorate this issue somehow. And let me just draw a schematic for how we'll do this. All right, so let's say here's frequency lambda q, and here's frequency lambda q plus 1. And I have RQ living here. What I've done is I've added this velocity increment. And I get new error terms whose minimum frequency comes from this thing. So let's say here's lambda q plus 1 RQ. And here's lambda q plus 1. And here's all my new error terms. What this estimate is saying is that these low frequency error terms are too big. I need to get rid of them somehow. And the way to get rid of them is, let's say we divide them up into bins. And I'm just going to fix them one at a time. So this WQ plus 1 didn't do a perfect job of sort of correcting this RQ. And so let's just come back and try again. So let's put a comma 0 on that guy to say that this was my first attempt. And I'm going to come back again with another velocity increment. And let's say just empty out this first bin. So I want this first bin to be empty. So my error terms now just live here. And what this means in practice is that my velocity increment is composed via a sort of secondary iteration via which I empty out all these bins one by one. So let's say WQ plus 1 equals some sum of WQ plus 1 comma P. And this parameter P ranges over some set of values, which is just the number of bins that I have. And for me, it will be independent of Q. That's important. All right, so.
And those bins, they go up.
Yes, they have to go.
Arithmetic projection in an arithmetic fashion. I mean, like you're drawing them exactly equal. They equal.
Yeah, you have some. So maybe they're equal on a logarithmic scale.
Logarithmic scale.
Yeah, you have some flexibility in how you choose the bins. That's yeah, I can explain that maybe in I guess 16 days. All right.
But the number is fixed independently of the
Absolutely.
Q at which you stay.
Absolutely.
So it's just maybe large, but a fixed number.
Large, but a
So
fixed.
the inner iteration is not.
Say again?
The inner iteration is not becoming more and more steps.
No.
It's always a fixed number.
Absolutely not. All right. So this is what we see in the oscillation error. And I want to say something now about the transport error. So I guess I erased it, but just like oscillation, it will come out of some inverse divergence operator. And what it looked like was the following. All right, so I have to estimate this thing somehow. And the first thing to notice is that this is linear in W. And that's useful because if I want to measure this in L1, which is where I measure my error terms, and it's linear in W, I can appeal to the L1 norm here. And this is small. So this gains RQ. This is part of why you want to take RQ to be small, because if RQ were not small, so let's say if you took RQ equals 1, you could do some heuristics which would exactly spit out that alpha is less than a third. So what I'm saying is that without the intermittency, there's no way that I can think of for this error term to cross the 1/3 threshold, which makes sense because otherwise I'd be violating the Constantine-Error TT rigidity theorem. So I should expect to use the intermittency somehow to my advantage, and here's one way in which we do. All right, so the second main tool that we use to analyze this is the following. This differential operator is always costliest if it lands on something high frequency. So I want dt plus uq dot nabla of this script w to be 0. And so what I should do is compose script w with some flow map phi, which solves, all right, so this is a function of tx. And it solves the transport equation. Oops. And I'm going to set it to be equal to the identity at some time. So phi, let's say t equals 0 equals the identity. And then if I compose w with phi and I take the material derivative at 0, and that's great. But the problem is that stability of this transport equation requires information on the Lipschitz norm of the velocity field. And this is not something that I propagated inductively. I just propagated information. I guess I should have said in L2, but that's what I'm propagating. And I can convert L2 information to pointwise information by Chebyshev. So I could say that if here I have my time and space, maybe I have 3 regions. One in which, let's say, WQ is like lambda q to the 0. Maybe it's of order 1 here. And maybe here it's lambda q to the 1. And here it's lambda q squared. And I can say how big each of these regions are just by Chebyshev. All right, so what do I do then in each of these regions? So this quantity determines the time scale upon which solutions of this are stable. And so I divide up this region according to that time scale. And what I put here is some flow map. So let's say phi 0, because that's the size of WQ in terms of lambda q. And let's say this is the first one. And then here I have a second flow map. And in this region, I have similarly, let's say phi 1, 1, etc. So these blocks are shorter in time because gradient of UQ is bigger. And similarly here. And each of these flow maps then should be equal to the identity. Let's say J comma K. It should be equal to the identity at some time in its in this block. So let's say T J comma K sometime. And I should also have cutoff functions which restrict each of these flow maps to only be relevant on this block. So
These are not necessarily constant in time.
say again?
These regions are not necessarily constant in time.
Not necessarily, no. I guess I drew it that way for simplicity.
Not even invariant under the flow maps.
They obey good material derivative estimates, but yeah, they're not quite invariant. So let's say my real perturbation now should look like square root of R cubed script W. It gets composed with some flow map, and then it has some partition of unity function eta, which tells me that I'm only looking at this guy on the support of this block.
But how do you handle the various interactions? Because they might be pretty messy. No?
Absolutely. So that's I guess the last thing that I'm going to say is what do you do in the regions of overlap? So let's take some region of overlap. All right, so in this region of overlap, I have a few different flow maps, each coming with its own set of pipes. So let's say I have some pipes here, and I have some pipes here, and I have some pipes here. And they all move, and they end up in this set at some point in time and space. And here, they're sort of deformed and not straight. And the problem with this type of picture is that these pipes could intersect. So we have to prevent intersections. And the way we prevent intersections is by appealing to the sparsity. So in this picture, there's no reason for me to have put the blue dot in the center of this cell. I could move it around somewhere else. And that's just saying that the sparser my object is, the more empty space there is in between. And I'm going to use that empty space to essentially find a smart placement of these objects, which prevents intersections. So let's say, how does this work? You just discretize in space. So I only consider this problem one at a time. And on each of these little pieces, I appeal to the sparsity. So sparsity. And I guess I'm out of time, so let me stop there and thank you for your attention.
Questions?
How much viscosity would this, could you potentially add?
So the problem is that these W's, they don't solve Navier-Stokes. And so the Laplacian has to get treated as an error term. And it's linear, which means that you can use this RQ to help beat it, but you have to use a lot of intermittency, which sort of it wrecks the value of alpha down to something tiny.
But you couldn't, with this scheme, it wouldn't work with Navier-Stokes at all. In the way,
Sure, okay,
in the
sure.
way,
Yeah.
at least in the way that my paper with Vlad
Yeah.
Because the frequencies are so close together, you couldn't use the trick we have.
Yeah, so
A different trick.
yeah, the sparsity that I've written here is actually not even enough to defeat the Laplace, and you have to dig out a little extra from somewhere.
So if you draw the spectrum, the 5/3 curve, how it would look for the solution?
The number A has to get chosen at the end to be somewhat large, and B is just a little bit bigger than 1, but it's still bigger than 1. And what that means is that most of the frequency shells are probably somewhat empty. I guess that seems like that same problem seems to plague most convex integration schemes from what I can tell.
So it would be kind of like oscillating the.
Yeah, I think so. I mean, and you would have some sort of centered at these frequencies lambda q, you would see something which was decaying a little bit faster than the 5/3 law would suggest.
So for that picture in which you are preventing intersections, I was just wondering, because we have a similar problem in the paper with Hyunju, but like we have to be kind of very careful, no? Because you have this discretization, you start like, I don't know, choosing this one here, then choose the next one, then choose the third one, but like you have to adjust it kind of carefully. And for us, it's important that the grid over which we're discretizing is like uniform. But here your grid is not really uniform because, as Laszlo said, no, you have different regions which are different size. So how do you go with that?
I guess what you should really do is, so I drew sort of one region in which I'm solving this problem, and then I just have more regions.
So you kind of discretize on a regular grid, which is like finer than all of this?
You discretize at a scale which is, so the thickness of these blobs is lambda q inverse. Anything smaller and the oscillation error would ruin you.
Yes, everything smaller and ruin you. But somehow those big regions in which you're using more or less the same flow, you still actually discretize in small anyway.
Yeah.
Even though you wouldn't need it somehow, but in that way, like, you know, your grid is really kind of uniform.
Yeah, you kind of do need it because, you know, as this set gets larger, there's more of these objects that I have to miss, and you know, that's a constraint then.
And if I may ask another question, so why, because you have to make these computations for all of them, because you're transporting all of them, of the blocks.
You mean there's different flow maps in here, or what do you mean?
Well, you have, because of your very first step, no, I mean, you have these like sum from, say, P, which is going to 1 to P max. So you actually have different transport errors for the different guys.
Correct. So what I guess you're saying that there could be some old pipes in here, which the next generation in P has to also avoid interacting with.
Yes.
Yes, we can use the same trick.
But not only that, somehow, like, you know, each of the error terms would look a little bit different, right?
No, we transport everything by UQ.
But their size might be a little bit different also, like, you know, their scale is a little bit different. So do you all get the same errors, or is there like, I don't know, one guy who's the worst error of all of those P?
So there's constraints with in terms of how much intermittency you use for each of the P's. And in order to get H1/2, you have to use a minimum amount of intermittency. But if you're not trying to propagate any regularity estimates above L2, you can sort of use as much intermittency as you need. And somehow that doesn't cost you in the context of an L2 scheme. So I guess the worst error term is just the oscillation error term, because that's where the 1/2 mainly comes from.
But those pieces, like when you transport them, you more or less get the same errors, or like?
You mean if I look at
Yeah.
DTQ? Yeah, so
So when you apply to each of these WQ plus 1P, I mean, it's like one guy gets the.
You can make it so
the biggest loss, or are they more or less all the same?
you can make it so that they're all the same, but as P approaches P max, you get something which is sharp with 1/2 because you stop gaining in the L1 norm because you're using less intermittency at the end.
Okay.
So I guess the last one is the worst.
So what's the for the total sum in P for the WQ plus 1, the support, is it the whole lambda Q box, or is it still a sort of
The spatial support,
yeah, it's just a spatial support.
yes, it's everywhere in the torus.
It is everywhere.
Maybe a bit more basic. So you showed the flexibility for the alpha less than 1/2. The best results for which I have conservative nature. So I guess I could just apply sublet embedding and the Constantine ETD result.
Yeah, that's basically the best.
That's the best. Okay.
But wouldn't that be 5/6?
Yeah.
It is.
Yeah, 5/6. So there's still a gap.
There's still a gap.
How do you reconcile all this with the numerics? Because okay, the numerics actually was saying what 0.36. It's not even half.
Right. So I guess you would say that
Better than nature. We're much more efficient.
We're much more efficient than nature. Wow. That doesn't look very plausible.
I think one should continue. Like I only picked certain properties in turbulent flows and tried to build solutions exhibiting those properties. I think the goal would be to pick another property and try and keep some of this. So let's say pick the 4/5 law. Say that I want to build something which has this intermittent nature in L2, but still satisfies the 4/5 law. That would be the natural next step.
So what's the estimate?
This one is not satisfying it.
What's the estimate here you get for L3?
So we didn't make the computation, but I think the LP regularity of U itself is something like L4-ish. L4, L5, somewhere around there. So the third order structure function exponent is a little bit bigger than 0, but I don't think it's that close to 1/3.
Okay. So the possibility would be that if you actually try to accommodate for that, then you will lose a lot in the half, kind of.
Perhaps it remains to be seen.
I think you just make your life more difficult. I don't think you necessarily lose a half. It's more difficult.
So you don't think that is the reason why you don't see a?
It shouldn't. I don't think you should necessarily expect to get the same exponent as what they get in physics experiments. Like you should be able to do whatever because
Yeah, I mean,
constructing the flow yourself. It doesn't have to agree with.
I would say that, I mean, these solutions don't satisfy the local energy inequality that Hyunju was talking about.
0.36 isn't a law either. Like there's different intermittency exponents depending on different experiments. There's no one answer to that. So even in physics, you can imagine strange settings in which you get a much larger.
So it's not something that you could guess from, say, like, okay, I want this sort of estimates, and then there's some sort of compatibility, and then it's going to crank up a number.
Yeah, I think
it looks much murkier than that.
Yeah, I think it's perfectly realistic to get 1/2 for the L2 and 1/3 for the L3. We can't obviously do it, but you can imagine such a scheme working. 6/5, I mean, there's an obvious reason why 1/2 is like in terms of the method, it is a critical thing, which is the oscillation error that there's something inherent in these quadratic convex integration schemes that 1/2 is I mean, you see it even in Nash embedding. Like
Right.
1/2 is kind of a key number in all of this convex integration schemes related on these quadratic nonlinearities that appear. So that's a bigger threshold that I don't know. We don't have any clue of how you would surpass 1/2 in order to get 6/5. That's not to say that it's not possible, but that's a bigger obstruction, I'd say.
But I don't know, maybe you looked into this, but okay, I mean, this 3/6 is not universal, but it's never much bigger, right? I mean, it's and the different experiments, but it's I mean,
sure, but in math, we can
law
create-
is not exact, but it's pretty close in many experiments.
But in math, we can create outliers, and it's harder to create outliers in physics experiments. You can find strange settings in which outliers happen. But in math, we can decide to go down that path.
So you would say, for instance, the fact that we have the Hölder, that's a huge outlier, right? Compared to.
Yeah, I mean, I think, didn't
Compared to
Theo,
what I guess people would expect for large B.
yeah, I think Theo said 2 weeks ago that one might even just expect bounded. But I don't think that, I don't know if that's for certain, but that's just one guess. But no Hölder regularity.
Oh, not Hölder, but just bounded.
I think that's what, I guess that was part of the discussion at the end of Hyunjin's talk.
Well, okay, if there are no other questions. Thank you.